Hi, everyone. Welcome to Lecture 3 of Chapter 7. And before we start going over any new material, I think it's a good idea to review a little bit of what we covered last time. So last time we learned that in order to figure out whether we have sampling error or sampling error plus something else, we need to look at the HO distribution. Remember, HO says null, nada, nothing. The only thing that you have in your samples is sampling error. And the hypothetical distribution that you're looking at here represents all the values of a test statistic that you might get, and that test statistic could simply reflect HO. In other words, null, nada, nothing, sampling error. All right, so along the x-axis, we have different values of the test statistic. Remember, the test statistic is what gets calculated when you go through the steps of hypothesis testing. You're going to pick a statistical test, and that statistical test at the very end is going to give you a number. And that number, regardless of which statistical test you use, that number is called your test statistic, or just TS for short. So HO, along the x-axis, we have test statistic values, TS values. And HO is saying that you can get any of these test statistics, and they could simply be reflecting sampling error, null, nada, nothing. Of course, some of these test statistics have a very high probability event on HO. So these are the TS values that are in the middle of the distribution. In other words, these are very, very close to 0. So if you get a very small TS value, it's a high probability event on HO and probably just really does reflect sampling error. But as we go out to the left tail, the values of the TS are increasing, and they're becoming increasingly less probable. So if you get something way out in the tail, whether it's the negative tail or the positive tail, these TS values are pretty large, and they have a very low probability of occurring, which means they could, in theory, be just reflecting sampling error, or maybe because they're such a low probability event, we should actually reject HO and say they must belong to some other distribution. And let's see, what else did we learn? We learned that once you draw this hypothetical distribution, what you need to do is calculate your TS and see where it falls. Okay, so it's going to fall somewhere here. It has to, because this distribution goes from negative infinity to positive infinity. So if your TS falls in a tail, well, then you know it's got a low probability of occurring, right? But we want to make sure that the probability of your test statistic is less than either 5% or 1%. You learned that when you do hypothesis testing, you choose alpha, which is called level of significance. If you choose an alpha of 0.05, what you are saying is you are only going to reject HO if the probability of your test statistic is less than 5% on HO. All right, so you got to figure out, is my test statistic, is the probability of my test statistic less than 5%? All right, if you were choosing an alpha of 0.01, then you're saying that you will only reject HO if the probability of your test statistic is less than 1% on HO. So let's just work with alpha 0.05. You're only going to reject HO if your test statistic has less than a 5% chance of occurring. Well, what that means is you have to figure out what would be the two TS values, okay, a negative and a positive. What would the two TS values be in order to give you the middle 95%? of the distribution. Well, now I'll explain why that's important. But once you figure out what this TS value is and this TS value is, then they become your critical values. This one will be negative, this one positive. They're going to be the same number, only just negative and positive. Now you have defined the middle 95%. And remember, we get these values here by looking at a table, all right, or an app online. Just Google it. But you want the middle 95%. The reason why you're looking for the middle is because now you have 5% left over, right? And that means that if you have two tails, which of course you do here, you're going to have 2.5% in this tail, 2.5% in that tail. Now you can say that as long as your test statistic is bigger than this negative critical value, in other words, it's more towards the left, if it's bigger than the negative critical value, then it's going to fall in this part of the curve. Similarly, if you get a test statistic that is bigger than this critical value, that means it falls in this part of the curve. And do you remember what these areas are called? These little areas in the I just gave it away. These are called the rejection zones. All right. So as long as you get your test statistic to fall in a rejection zone, you know that for alpha 0.05, the probability of your test statistic has to be less than 5%. Now remember, you say less than 5%. You have to report the total area for the rejection zone. You can't say my test statistic has less than 2.5% chance of occurring because you didn't know if your test statistic was going to fall on this side or this side. So we report the total rejection zone area. All right. If let's say you were using alpha 0.01, then you would just have 99% here, and then 0.5% here, and 0.5% there. And you would need to find out your new critical values. So your critical values are just simply, they are, call them special values of the TS. They are the values of the TS that will give you that middle, either 95 or 99%. And once you figure them out, they are called critical values. So any TS that falls in a rejection zone is going to be significant. That's what we say. It is significant. And we reject HO. Any TS, same thing on this side. If your TS is bigger than the critical value, then we say the results are significant and we reject HO. All right. Now, if your test statistic happens to fall in between, then you're going to have to say that your test statistic is not significant and you retain HO. All right. Now, remember that even if we reject HO, let's say our TS is here. Well, we're assuming that it must be a higher probability event on some other distribution. What's that other distribution called, by the way? Remember the two competing hypotheses? That other distribution is HA. HA is saying you have more than sampling error. So you have sampling error, but something else on top of that. So if we're rejecting HO, we're assuming it's got to be a higher probability event on HA. And we could be right. Maybe we correctly rejected HO. But remember, your test statistic still has a slim possibility of belonging to HO. So we might be making a mistake. So if we reject HO, thinking we've got a significant result and we've got more than sampling error, but it still belongs to HO, even though it's that small probability, if it still belongs to HO, then we've made a type 1 error. Okay? And so we make all of our decisions about whether we're going to reject or retain HO. We make all decisions whether we're going to reject or retain HO based on where our test statistic falls on HO. All right, and that is why we call HO the working hypothesis. We're going to base all our work, all our decisions off of this hypothesis. All right, so that's about as far as we got last time.